And welcome back to the final section of Chapter 9 in our textbook, 9.6, which some of you will be happy to hear doesn't really introduce any new math, arithmetic skills. It's more about applying what we've already learned about logarithms and exponentials in real-world functions. So the title of this section is Exponential Growth and Decay, and the first part of this video is just going to be going over some vocab. How do we know, based on a word problem, yes, love those, if we are looking at exponential growth or decay? Well, growth, a quantity is growing. Value of a collectible appreciates. That means it's going up in value. Amount of bacteria increases. Those are all keywords talking about exponential growth. Are they the only words that could be used? No. But those are all keywords that you should be on the lookout for, anything that makes it sound like a quantity is growing. Versus a quantity is shrinking. Value of a collectible depreciates, means it goes down. Amount of bacteria decreases. That would be decay. We've kind of already seen and talked about growth and decay. Now we're just going to be analyzing and pulling these words from word problems to know what kind of equations we should use. So as it turns out, there are going to be two, I'm going to put, well, no, I'm going to keep it right here for now. There are going to be two main equations used for exponential growth: fixed growth and continuous growth. And they have some similarities, but they're definitely not exactly the same. So on the left, we have fixed growth. Y equals A times 1 plus R to the tth power. A is still the starting amount, R is still the rate, T is still time. And how do we know we're dealing with fixed growth? Well, fixed means it grows by the same amount each time interval. So those examples below, switch to a yellow highlighter. Population grows at 2% per year. That means every single year it grows by 2%, the same amount. Or home value increases 4% per year. Interest grows at 0.15% per month. When you see per, when you see every month or each day, a lot of times that has to do with fixed growth. Versus on the other side, we have continuous growth. Y equals AE to the KT. A is still the starting value, T is still the time, but K is some constant. Constant for each problem. It'll stay the same through that whole problem. And it's just some constant that makes the equation work out nicely for the scenario given. So how do we know if something is continuous growth? Well, that means it's not growing just at one time per year. Population grows all the time, all throughout the year. So if it just says population growth from 2010 to 2012, it doesn't say it grew by this much per year, per month. That's just continuous. Population is growing. Something increases according to this equation that, hey, looks just like our continuous growth equation. Or if it just says bacteria reproduce exponentially, just saying, hey, they're increasing, they're reproducing exponentially. We're not going to say this much per day, per minute. If it doesn't give that very distinct fixed time interval, it's going to be continuous growth. If it does, fixed growth. And a really similar conversation to be had with decay. Exponential decay in the fixed category. Caffeine disappears at 11% per hour. Car value decreases 0.13% per month. Again, each week. So if it happens at a very set time interval, it's going to be fixed. And in this case, fixed decay has the exact same equation as fixed growth, except 1 minus R in those parentheses instead of 1 plus R. Continuous decay, same exact equation as continuous growth, except there's a negative in front of the K value. Y equals AE to the negative KTth power. And again, this is where in our word problem, we see something and it doesn't really say decreased by this much per day or each year. It's just a little more nebulous. It's just carbon decays exponentially or atom decay from this year to this year. It doesn't say per year, each year, every year, anything like that. So these four equations you need to know when to use them. And so we're going to see 4 practice problems, 1 for each equation, and see when to use them, and then just refresh the skills we've been working on the last few sections. How do we solve equations with ease in them, with exponentials, variables we need to get down, all those sorts of things. So first question, a store is offering a clearance sale on a certain type of digital camera. The original price for the camera was $198. The price decreases 10% each week until all of the cameras are sold. How many weeks will it take for the price of the cameras to drop below half of the original price? So what this one is saying is, I want to highlight one value here. One kind of phrase. The price is decreasing at 10% each week. That's a very set, fixed amount per week. And so what is that saying? That's saying we should use our fixed decay equation. I know it's decay because it's going down, decreasing, right? So that right there tells me fixed decay. So first thing I'm going to do is just copy down that equation. Fixed decay, y equals a times 1 minus r to the tth power. So what is the starting amount A? Starting amount, we were told the original price was $198. And it decreases, the price decreases 10% each week. So 10% as a decimal, 0.1. I'm asked how many weeks will it take. So I know I'm looking for t, but that means I need to know y. So it says how many weeks will it take for the price of the cameras to drop below half of the original price. So what I want to know is, what is half of the original price? 198 divided by 2. I want to know when we hit $99, because once we hit $99, half the original price, anything after that will be below. So I've got my equation all written out. Let's solve. Divide by 198. And that comes out to be 1/2. I just did that on a calculator, equals, I hope you're okay with me writing 0.9 to the tth power, 1 minus 0.1. Okay, so I have a variable in an exponent, that t is in the power. How am I going to get it out of there? I'm just going to take the log of both sides. Remember that power property is then going to allow me to drop this t out of the exponent down in front. So I'm going to move over here where I have a little more room. Log of 1/2 then equals t times log of 0.9. Divide by log of 0.9 on both sides. And I get, there it is, log of, I'll type in 0.5 for 1/2 divided by log of 0.9. I get 6.5788. 6.5788 equals t. Now, before I circle this and move on, in the context of this problem, it sounds like maybe at the beginning of each week, Monday morning, the store knocks it down another 10%. So how many weeks will it take? Well, it takes over 6.5 weeks, but it's probably not going to happen in the half week. I would probably add a note and say, so in a real world context, it'll take 7 weeks for it to drop below half of its original value. About 6.5, but I don't think the store is going out at 0.5788 of a week and saying, okay, drop it, let's get it to half. Probably about 7 weeks, just in the context of this problem. So again, no real new math skills there, but an example of identifying what equation we need. We needed fixed decay because it decreased 10% each week. How about this next one? In 1910, the population of a city was 120,000. Since then, the population has increased by 1.5% per year. And that should be setting off fixed growth alarm bells in your head. Per year, it's going up, fixed growth. If the population continues to grow at this rate, when will it be doubled? So fixed growth, y equals a times 1 plus r to the teeth power. Starting value was 120,000 people in this town. 1 plus 0.015, because 1.5% as a decimal, to the teeth power. And we are looking for when the population will be doubled. And I know that double 120,000 would be 240,000. So we've set this equation up. I want you to work it out. I'm going to pause and work it out, and I'll unpause when all my work is on the screen. All right, my work is now on the screen. I got around 46 years, 46.5555 years, I think. Make sure I got that right, yep. From log of 2 over log of 1.015. And so in blue, I also put the answer to the question. The question was, when will the population be doubled? Well, if we started this problem in 1910, 46 years later, so about 1956 or 1957, because it was about 46 and a half years. So right around then is when the population will be doubled. One quick thing I want to mention is instead of using log of 2 over log of 1.015, if I said natural log of 2 over natural log of 1.015, notice it comes out exactly the same. So when we're doing this, we can use either log that we want. Log base anything, really. Those are just the two on my calculator, so those are the two that I would choose between. All right, 2 down, 2 to go. And this one introduces a little bit of vocab defined there in the parentheses. It says, what is the half-life of a substance if it decays according to the equation y equals AE to the negative 0.2666 t, where t is in years? Now, looking at this equation, I know that we're talking continuous decay. Not that it matters too much because they gave us the equation. But what is this deal with half-life? It's actually an interesting scientific concept that plays out in the real world where, let's say, and I'm just going to make a graph because I think it demonstrates it nicely. 1, 2, 3, 4, 5, 6. Let's say that I start with 6 grams of a substance. The half-life is how long it takes for half of that substance to decay. So after 1 half-life, I'm down to 3. After another half-life, I'm down to 1.5. After another half-life, I'm down to 0.75. And you can see the exponential curve there. But what's really fascinating is that each of these half-lives is exactly the same amount of time. So if it takes 10 years to go from 6 to 3, it'll take 10 years to go from 3 to 1.5. Even though not as much is decaying, half of the substance is decaying, and it will take that same amount of time, that half-life. So in terms of our equation, which was given to us, y equals AE to the negative 0.2666 t, there's that k value, the constant. Here's the fun fact, it doesn't matter how much we start with. As long as our current value, our y value, is half of that. For simplicity, I usually just start with 100. I say I start with 100 grams of something, and that means I know that 1 half-life will have passed if I have 50 remaining. I could start with 10 and 5, or 20 and 10, or 1,500,000, whatever I want. But when I solve this, the very first step is why it doesn't matter what I start with, because when I divide by 100, and I had 50 as my current value, no matter what I start with for a half-life, we'll always get 1/2 over there, hence the half-life. 1/2 equals e to the negative 0.2666 t. How do I get rid of an e? I'm going to natural log both sides. natural log of 1/2, natural log of e to the negative 0.2666t. So natural log of 1/2 equals negative 0.2666t. Divide by that negative 0.2666, that k value. And we get that t equals, let's plug it in a calculator, natural log of 1/2 divided by negative 0.2666, about 2.6000 years. I think it said it was in years. If we round, 2.6000 years. So every 2.6 years, half of the substance is going to decay. And this is, like I said, a thing in real life. If you've heard of carbon dating, this is how they date things based on how much carbon remains in them, because carbon has a very, very steady and consistent half-life. And so based on how much was in it at one point, based on how much is in it now, we know how much time has passed. One more problem for today. It says, for a certain strain of bacteria, K is 0.872, we're given the K value, when T is measured in days. Using the continuous growth formula, how long will it take 9 bacteria to increase to 738 bacteria? We were told continuous growth. So I'm going to write that down, y equals a e to the kt. And I was told K was 0.872. What was my starting number of bacteria? 9. My ending, I want to know how long it'll take to get to 738, e to the 0.872t. And now it's not a word problem any longer. It's just a solve this exponential equation problem. Try it on your own. Try it on your own, pause the video, and then come back and see if your work matches mine. All right, on the screen now is my work. The key step, probably right here, when I got rid of the e by taking the natural log of both sides. After which I divided by 0.872 and plugged in the calculator, and I got that t was 5 days roughly, 5.0536 days for 9 bacteria to grow into 738. So 9.6 is all about these word problems, just different scenarios when we might be using exponential growth and decay. We have those 4 equations, continuous growth, continuous decay, fixed growth, fixed decay. You will need to be able to look at a word problem and identify which equation should I use. If it says per year, each day, per month, it's going to be fixed and growth or decay if it's going up or down. If it's more nebulous, or if it gives you the equation and it matches, it has an e in it, and matches our continuous equations, obviously use that. But this is kind of the end, just wrapping up of chapter 9, using these exponentials and these logs to solve equations in real world scenarios. I know how much everyone loves word problems, but again, word problems are kind of the only ones worth solving because they are real world problems that you get a result out of, that you can do something with that answer instead of just turning in math homework. Although that's what you'll be doing with this, obviously. So take a look at your practice problems. If you have questions, let me know. Either circle them so you can ask them in class or contact me. But this is a wrap on chapter 9 from our textbook, Logarithms and Exponentials.